Next problem. This one we're looking for the power factor in this circuit. Reminder, the power factor is the cosine of the angle between the complex power and the real axis. So we have a 110 microamp current source feeding a load which is a 820 kilo ohm resistor in parallel with a 330 femtofarad capacitor. Don't use femto very often, it's 10 to the minus 15, the one below pico. But the only thing I can think of that might cause such a small capacitor in this circuit is if that capacitor is a parasitic capacitor in this resistor component. However, let's go and have a look at this. Now, useful thing to know about the complex power is that it is in the same direction as the complex impedance of the load. So, if we know the angle there, the phase angle of the complex impedance of the load, we know the phase angle of the complex power and can therefore work out the power factor quite readily. How do we get the complex impedance of the load? Well, it's an 820 k ohm in parallel with a 330 femtofarad. Complex impedance of 820 k is easy. Complex impedance of 330 femtofarads. That would be, using the formula 1 over j omega c, the complex impedance of a capacitor. That would give minus j over omega be 2 pi times the frequency in hertz, which would be 4 pi times 10 to the 6, times the capacitance, 330 times 10 to the minus 15, which requires a calculator, which gives me minus 241 kilo times j. Not exactly, but that's near enough. The complex impedance of two components in parallel like this, that would be the total impedance, would be the product of the two, which is 820 k times minus 241 kj, divided by the sum of the two, 820 k plus minus 241 kj, or just 820 k minus 241 kj. We want to know the phase angle of this complex number. Easiest way to do that is to express both the numerator and the denominator in polar coordinates, and then the angle of zt will be the angle of the numerator minus the angle of the denominator. The numerator, well, that's just going to be 120 k times 241 k times, well, in terms of its phase angle, it's going to be minus 90 degrees. It's entirely negative imaginary. It's down here on the Argand diagram. So that would be e times j to the power of, well, e times j to the minus 90 degrees. I'll work in degrees, it's a bit easier. The denominator here, then, is going to be some magnitude, which we're not really interested in. What we're interested in is the angle. If we take this denominator and think about it as a complex number, it's got a real part of 820 k, and it's got an imaginary part of minus 241 k. It's going down because it's negative. That means that the denominator as a complex number would be this point here. If I'm interested in that angle would be the arctangent of 241 divided by 820. The k's would cancel. And that is just, let's see, arctangent of 241 divided by 820, 16.4 degrees. So the denominator is going to be some magnitude, I don't really care, times e to the power of j Now this angle here is minus 16.4 degrees because it's clockwise from the real axis, e to the power of minus 16.4 degrees. That gives me a total complex impedance of some magnitude, which I don't really care, e to the power of j minus 90 minus 16.4. These are degrees, which in terms of the phase angle would be minus 90 plus 16.4 degrees, which is minus 73.6 degrees. So that is the angle of the complex impedance. The power factor is the cosine of that angle. So all I need to do is cosine 73.6 degrees, and that gives me 0.282. That'll do. That's that one.